Have you ever just looked at a giant skyscraper or a massive cargo ship and really wondered, how does that stay together? So often the answer is a weld, a single fused seam of metal that's holding incredible forces at bay. But what is it that gives that one little seam the power to hold up an entire bridge and keep a ship from splitting in two in a storm? Well, let's find out.
It's a pretty wild question when you think about it, right? What's the secret sauce? What makes one welded joint totally unbreakable, while another one becomes the single point of failure that brings everything crashing down?
It turns out the answer isn't something you can see with your own eyes. To really, truly get what makes a weld work, we've got to shrink ourselves way, way down and explore the invisible world that's hidden deep inside the metal itself.
So here's the game plan. We're going to dive into the secret life of welds, figure out the recipe for making them super strong, understand how they fight off breaking, uncover the hidden stress that tries to tear them apart, and then we'll take a peek into the future of welding.
All right, first up, let's go ahead and unlock that hidden blueprint inside the metal.
So the single most important idea for all of this is something called the microstructure. You see, every piece of metal is made up of these tiny little crystals called grains. And how those grains are arranged, their size, their shape, that creates the material's unique blueprint. It's just like a recipe. You change the ingredients, you change the process, and you get a totally different result.
And here's the crucial part. Size matters. A whole lot. Just picture it like this. A wall built from fine sand is way more packed and solid than one built from loose pebbles, right? It's the same with metals. When you have smaller, finer grains, you create way more boundaries between them. And these boundaries act like a super complex maze that makes it incredibly hard for a crack to find a straight path. All that complexity is what makes the material so much stronger.
Okay, so if having fine grains is the secret, how do engineers actually do it? How do they manipulate things to get that perfect structure? Let's get into the actual recipe they use to build that strength right into the metal.
Now this is where theory gets real. Check out this research from Weld and his team. They were looking at TIG welding stainless steel with different filler materials, and the results? They are crystal clear. One particular filler wire, the ER316L, produced the finest grain structure. We're talking just over 9 micrometers. That's about the size of a single human red blood cell. And look what that tiny detail did. It resulted in the highest hardness and, most importantly, the highest tensile strength by a long shot. 857 megapascals. Now, to give you an idea of what that means, that is like hanging over 8 tons. That's the weight of 2 full-grown elephants from a little patch of that weld, just 1 square centimeter in size. It's the perfect illustration of that direct link. Finer grains equal a ridiculously stronger weld.
But just making the grains smaller is only part of the story. To really push the limits of strength, engineers have a whole bag of tricks they can use to tweak that internal recipe even more.
For one, they can introduce these tiny, hard particles called precipitates. You can think of them like microscopic rebar, just reinforcing the metal matrix from the inside. Another wild technique is cryogenic treatment, using extreme cold. In fact, research from Minhas and their team showed this could boost an aluminum alloy's strength by a staggering 54%. And you can even add nanoparticles directly into the welding filler material, which helps create those awesome fine grains right from the get-go. All of these things work together to build a powerful, resilient internal structure. But, pure raw strength isn't everything. A weld can be incredibly strong, but still be brittle and shatter like glass. So what happens when that super strong weld gets hit with a sudden, sharp impact? Well, that's where toughness comes in, the ability to resist cracking and catastrophic failure. This quote here really gets to the heart of it. See, when a tough material finally breaks, its broken surface is covered in these microscopic dimples. These dimples are proof that the material stretched and absorbed a ton of energy before it finally gave way. And a finer microstructure leads to finer dimples, which means, you guessed it, better toughness. So it's not just if it breaks, it's how it breaks that tells the story. And remember those little rebar-like particles, the precipitates? They are absolute heroes here. When a tiny crack starts to form, it'll travel through the metal until, bam! It smacks right into one of these hard particles. That particle acts like a roadblock. It forces the crack to either stop completely or change direction, which burns up its energy and prevents a total catastrophic failure.
And we see this play out in the lab. A 2025 study on friction stir welding showed that just by optimizing the process, they could shrink the grain size by over 22%. And the result? A direct, measurable improvement in the weld's impact toughness. It's a simple equation. Better microstructure, better resistance to breaking. Period.
Now, even if you create the absolute perfect microstructure, there's an invisible enemy that can still ruin everything. We're talking about the hidden stress that gets locked inside the weld from the process itself.
It's called residual stress. I mean, think about it. Welding involves extreme heat. As the metal rapidly heats up and then cools back down, it's pulling and pushing on itself, creating this intense internal tug-of-war. That tension gets locked in. It can warp the part, or even worse, it can act like a preloaded weak spot that leads to failure years down the road.
And it turns out that how much heat you pump into the weld makes a huge difference. As you can see pretty clearly here, high heat processes tend to leave behind way more of that damaging residual stress compared to more controlled low heat methods. So minimizing this hidden stress is just as critical as maximizing the weld strength.
So, a huge focus in modern welding is finding clever ways to manage this tension. For instance, researchers are now using some pretty futuristic techniques, like applying high-frequency ultrasonic vibrations to the weld as it's cooling. These vibrations literally shake the stress out of the metal, relieving those hidden forces and making the final joint far, far more reliable.
And all of this brings us to the future. Where does all this incredible microscopic engineering take us next? The big takeaway, the whole point of all this, is a really simple but powerful idea. If you can control the micro world, you can master the macro world. The future is all about designing filler materials with custom nanoparticles, using AI and sensors to watch and adjust welds in real time, and using advanced treatments to perfect that microstructure. The goal isn't just to join two pieces of metal anymore. It's to create a joint that is perfectly, precisely engineered from the inside out for any job you can imagine.
It really just leaves you with this one last thought. From skyscrapers that can dance in an earthquake to impossibly lightweight spacecraft exploring other planets, the things we build are only limited by the materials we have. So what on earth will we be able to build next now that we can literally design those materials atom by atom?